December 12, 1942. Melun-Villaroche airfield, occupied France. A ground controller's log noted an unidentified four-engine aircraft descending through low clouds, its Wright Cyclone engines sputtering as propellers windmilled unevenly. Wehrmacht sentries ran toward the grass strip as the massive bomber settled onto French soil, its olive-drab paint and white star markings clearly visible through the mist. Lieutenant Paul Flickinger believed he had reached England after a harrowing mission over Rouen. Instead, his Boeing B-17F Flying Fortress, serial number 41-24585, had just delivered Germany its first intact example of America's primary strategic bomber. Within minutes, Luftgau commando staff surrounded the aircraft with rifles drawn, securing what would become the most valuable intelligence prize of 1,942. The bomber sat nearly complete, its 13 Browning M2 machine guns loaded, its Norden bomb sight sealed in its container, its self-sealing fuel tanks intact. German engineers would soon discover that this single aircraft revealed not merely a weapons platform, but a systematic approach to aerial warfare that Germany could observe, measure, and document, yet ultimately never match. The emergency landing at Melun represented the culmination of cascading failures that began over the skies of northern France hours earlier. Flickinger, flying with the 303rd Bomb Group's 360th Squadron, had participated in a mission targeting the Sotteville marshalling yards near Rouen. German fighters intercepted the formation over occupied territory, and accurate flak damaged multiple bombers. Flickinger's B-17F, nicknamed in some accounts, though documentation remains incomplete, sustained hits that severed hydraulic lines and damaged the oxygen system. The crew faced a choice familiar to bomber pilots over Europe: attempt the channel crossing with uncertain fuel and failing systems, or find the nearest field and land while the engines still functioned. Flickinger chose to land, believing through navigation error or confusion that he approached liberated or neutral territory. The grass field at Melun-Villaroche appeared suitable for emergency landing, and the B-17F's robust landing gear absorbed the impact as the bomber rolled to a stop on occupied French soil. German troops who secured the aircraft found the crew confused but uninjured, their bomber substantially intact despite combat damage. A field inventory documented the aircraft's condition. All four Wright R-182097 Cyclone radial engines remained operational, despite one showing signs of oil pressure loss. The turbo-superchargers that enabled high-altitude operations were undamaged. Every defensive gun position retained its Browning M2 machine gun. Ammunition boxes held thousands of rounds. The bomb bay was empty, ordnance having been expended over the target. Critical avionics, including radio equipment, and the classified Norden bomb sight, were present and functional. Luftgau Commando Paris received immediate notification of the capture. Orders arrived within hours to secure the aircraft against sabotage and prepare it for transport to Erprobungsstelle Rechlin, the Luftwaffe's central testing and evaluation facility in Mecklenburg. The priority assigned to this transfer was unusual for a single captured aircraft. Standard procedure would examine the bomber at local Luftgau facilities before deciding whether to forward it to Rechlin for detailed evaluation. But the B-17 represented unprecedented intelligence value. Since the type's combat debut over Europe in August 1942, Luftwaffe pilots had reported troubling characteristics. The American bomber could sustain extraordinary battle damage and continue flying. Its defensive armament created interlocking fields of fire that made traditional stern attacks suicidal. Formation discipline allowed bomber groups to concentrate defensive fire that destroyed attacking fighters. Within 7 days of the landing at Melun, Oberkommando der Luftwaffe headquarters in Berlin issued orders citing the captured B-17 for immediate central evaluation. This urgency reflected growing concern at command level about American strategic bombing capabilities. The Luftwaffe had designed its fighter force primarily for tactical support of ground operations and defense against medium bombers. The heavily armed, well-protected American heavy bombers represented a threat category German air defense had not anticipated adequately. Previous experience with British heavy bombers like the Short Stirling and Handley Page Halifax provided some baseline, but intelligence reports suggested the B-17 possessed defensive capabilities exceeding anything currently operational over Europe. The captured B-17F arrived at Rechlin in late December 1942 under heavy guard. Erprobungsstelle Rechlin had served as the Luftwaffe's primary aircraft testing facility since before the war, evaluating German designs and captured enemy aircraft. The facility maintained specialized equipment for comprehensive aeronautical evaluation. Test pilots with extensive experience flew captured aircraft to assess performance characteristics. Engineers measured every dimension, weighed every component, and photographed every system. Armament specialists test-fired weapons to document firepower. The B-17 received immediate priority attention. Hans-Werner Lerche, Rechlin's principal test pilot, was assigned to conduct flight evaluation once ground examination was completed. Lerche had established a reputation as one of Germany's most skilled test pilots, having flown dozens of captured Allied aircraft without serious incident. His methodical approach emphasized understanding aircraft systems thoroughly before attempting flight. He studied captured technical manuals when available, consulted with Rechlin's engineers, and spent extensive time in cockpits familiarizing himself with control layouts. The B-17 presented unique challenges. American cockpit design philosophy differed substantially from German practice. The instrument panel contained gauges and controls for systems German aircraft did not employ. The turbo-supercharger controls alone required careful study to understand proper operation. Before Lerche attempted flight, Rechlin's technical staff conducted systematic ground evaluation. Teams measured and documented the airframe's physical characteristics. The B-17F's dimensions were substantial by contemporary standards. Wingspan measured 103 feet 9 inches, length 74 feet 9 inches, height 19 feet 1 inch. Empty weight recorded at approximately 36,135 pounds, with maximum takeoff weight reaching 65,500 pounds in combat configuration. These figures made the B-17 significantly larger and heavier than any German bomber in operational service. The Heinkel He-111 H-16, Germany's most numerous medium bomber, had a wingspan of 74 feet, length of 53 feet 9 inches, and empty weight of approximately 19,136 pounds. The B-17 was an entirely different class of aircraft. The technical staff's worksheet documented armor protection that impressed German engineers accustomed to lighter defensive measures. The pilot sat behind a thick armored plate protecting against attacks from behind. Additional armor shielded the radio operator's position. The ball turret gunner position, though cramped and vulnerable by design, included armored components. Even the aircraft's self-sealing fuel tanks represented technology that Germany had developed but never implemented as systematically as the Americans. These tanks contained multiple layers, including vulcanized rubber that swelled when punctured by bullets, sealing small holes and preventing catastrophic fuel loss. German self-sealing tanks existed, but were less sophisticated and less reliably effective. Engineers cataloged the defensive armament station by station, documenting what would become the most significant finding of the entire evaluation. The B-17 F-mounted 13 Browning M2 50 caliber heavy machine guns positioned to create interlocking fields of fire, covering approaches from virtually every angle. The nose section carried two cheek-mounted guns, one on each side, operated by the bombardier or navigator. These guns could engage fighters attacking from the frontal quadrant. The dorsal turret position atop the fuselage, just behind the cockpit, mounted 2 guns in a power-operated turret, allowing 360-degree traverse and substantial elevation range. The ventral ball turret, suspended beneath the fuselage, contained 2 guns operated by a gunner curled into the spherical enclosure. This position provided coverage of the lower hemisphere and could track fighters attacking from below. 2 waist positions, one on each side of the rear fuselage. Each mounted a single gun operated by gunners standing at open windows. These positions covered the beam approaches. The tail position mounted 2 guns operated by the tail gunner, occupying a cramped station at the aircraft's extreme rear. This position defended against the traditional stern chase attacks that German fighter pilots had employed successfully against earlier bombers. The total defensive battery of 13 heavy machine guns represented a quantum increase over previous bomber types. British heavy bombers typically mounted 7 to 10 guns, usually a mix of rifle-caliber weapons and occasional heavier types. German bombers rarely carried more than 6 defensive guns, accepting lighter armament to maximize bomb load and performance. The B-17's designers had prioritized defensive firepower, accepting weight penalties to create what German analysis would characterize as a flying fortress, a name the type had already acquired in American service. Rechlin's armament section calculated theoretical firing rates across all 13 positions. Each Browning M2 had a cyclic rate of approximately 750 to 850 rounds per minute, depending on condition and ammunition type. If all 13 guns fired simultaneously, the B-17 could theoretically deliver approximately 160 rounds per second into surrounding airspace. This figure assumed perfect mechanical function and synchronized firing, unlikely in actual combat, but the potential maximum firepower was nevertheless staggering compared to any bomber previously evaluated at Rechlin. Ammunition stowage impressed the evaluators as much as the guns themselves. The captured B-17F carried over 11,000 rounds of .50 caliber ammunition distributed across the various gun positions. Some positions held 425 rounds per gun, others slightly more or less depending on space constraints, but the total ammunition load allowed sustained defensive fire throughout prolonged combat. By comparison, a Focke-Wulf WF-190A4 fighter carried 900 rounds total for its 2 7.92 mm machine guns and 500 rounds total for its 2 20 mm MG-151/20 cannons. A B-17 carried more ammunition than 11 German fighters combined. The ammunition itself revealed American manufacturing quality. German armorers examining the rounds noted consistent dimensions, precise machining, reliable primers, and uniform powder charges. Quality control appeared exceptional. German ammunition production, though generally adequate, increasingly suffered from resource constraints and the employment of forced labor with declining skill levels. American ammunition showed no such compromises. Every round examined met specifications precisely. The Rechlin Technical Report, compiled over several weeks, documented findings that circulated through Luftwaffe command channels with increasing concern. The B-17 represented not merely a larger, better-armed bomber, but a systematically engineered weapons platform designed specifically for survival in hostile airspace. Every element of the design prioritized combat effectiveness. The armor protected vital crew positions and systems. The self-sealing tanks reduced fire hazards. The defensive armament created overlapping coverage zones. The robust structure absorbed battle damage. The reliable engines continued functioning despite hits. The comprehensive instrument suite allowed precision navigation and bombing. But perhaps most troubling was the realization that this was not an experimental aircraft or limited production type. Intelligence reports indicated the B-17 was entering mass production at multiple American factories. Boeing's Seattle plant produced B-17 seconds, alongside Douglas facilities in Long Beach and Vegas plant in Burbank. Combined production was accelerating rapidly. If early intelligence estimates proved accurate, hundreds of these bombers would soon be operating over Europe, each carrying the firepower documented in the captured example. The Rechlin file reference RL 3/493 summarized the gun arc analysis that had occupied armament specialists for days. Using detailed measurements of gun mount positions, traverse limits, and elevation ranges, the engineers constructed geometric charts showing zones of fire coverage. The tail guns could engage targets from dead astern through approximately 90 degrees to either side, though effectiveness decreased at extreme angles. The waist guns covered the beam, approaches with substantial overlap in their fields of fire. The ball turret covered the lower hemisphere completely. The dorsal turret covered upper approaches and could assist waist guns against beam attacks. Most significantly, the nose guns provided frontal defense, a capability that previous bombers had lacked or possessed only weakly. Traditional stern chase attacks, where German fighters approached from behind to minimize exposure to defensive fire, would face the heaviest concentration of B-17 defensive guns. The tail position, waist guns, and potentially the ball turret could all engage a fighter making a stern attack. German pilots reported that closing to effective firing range, typically 300 to 400 meters, resulted in flying through a cone of defensive fire so dense that hits on the attacking fighter were virtually certain. Initial geometry charts prepared by Rechlin analysts demonstrated that no standard single-engine stern attack offered survivable margins inside 400 meters against a properly defended B-17. The volume of fire was simply too great. A fighter attacking from the rear would face at minimum 4 heavy machine guns, possibly 6 or more if multiple positions could bear on the target. Even if the German pilot achieved hits on the bomber, his own aircraft would likely sustain damage during the attack run. And the B-17's armor and robust structure meant that scoring hits did not guarantee bomber destruction, while even minor hits on German fighters often caused critical damage to cooling systems or control surfaces. Berlin received Rechlin's preliminary report in January 1943. General Adolf Galland, commanding the fighter forces as General der Jagdflieger, studied the findings with professional concern. Galland had accumulated extensive combat experience before assuming his staff position and understood tactical realities better than many officers. The Rechlin data confirmed what frontline pilots had been reporting. The B-17 was a formidable opponent that could not be engaged using conventional tactics without unacceptable fighter losses. Galland's assessment, later referenced in his post-war memoir Die Ersten und die Letzten, acknowledged that the B-17's defensive capability exceeded that of any known bomber type. German fighters possessed advantages in speed, climb rate, and maneuverability. They mounted heavy cannon armament, capable of destroying bombers with relatively few hits. Experienced German pilots were skilled in deflection shooting and attack techniques. But these advantages meant little if the fighter could not approach the bomber without flying through defensive fire that would destroy the attacker before weapons could be brought to bear effectively. The challenge was geometrical as much as tactical. The B-17's armament created a defensive sphere around the aircraft. Every approach vector faced multiple gun positions. Stern attacks faced the heaviest fire concentration. Beam attacks exposed the fighter to waist guns and turret fire throughout the approach. High side attacks faced the dorsal turret and potentially the ball turret as the fighter passed beneath. Diving attacks faced similar problems. Only one approach vector appeared to offer reduced exposure to defensive fire. A head-on attack, approaching the B-17 from dead ahead, would face only the nose guns initially, 2 weapons compared to the 6 or more positions that could engage from other angles. This frontal approach created different problems. Closure rates in a head-on attack approached 400 to 500 miles per hour, as the fighter's speed and bomber's speed combined. This gave the attacking pilot perhaps 2 to 3 seconds to aim, fire, and break away before collision. Deflection angles changed rapidly at such closure rates, making accurate shooting extremely difficult. The risk of collision was substantial, requiring precise timing and nerve to hold the attack until within effective firing range before breaking away. And if the German pilot broke too early, his shells would miss. If he broke too late, collision became likely. Yet the mathematics appeared more favorable than stern attacks. Frontal attacks would expose the fighter to defensive fire for perhaps 2 to 3 seconds total. Stern attacks required 15 to 20 seconds of exposure, while the fighter closed from initial firing range to point-blank range. Even with lighter defensive fire forward, the briefer exposure time made frontal attacks tactically preferable. Galland circulated tactical notes to fighter units recommending evaluation of head-on attack methods. The doctrine was dangerous, demanding skill and courage, but appeared to be the only approach that offered reasonable probability of success against B-17 formations. Hans-Werner Lerche began flight evaluation of the captured B-17F in January 1943 after ground examination was substantially complete. His flight log recorded takeoff weight, manifold pressure settings for the Wright R18209-7 engines, and turbo-supercharger operation parameters. A Messerschmitt Bf. 109 chaseplane formed up on the bomber's wing to observe and document flight characteristics. Lerche noted immediately the substantial difference between the American bomber and German aircraft he had previously flown. The B-17 was heavy, requiring careful attention during ground operations. Taxi speed had to be controlled precisely. The brakes, while effective, required familiarization to avoid excessive application that might cause problems on Rechlin's grass surfaces. Takeoff required full power on all 4 engines. Lerche advanced the throttle smoothly, monitoring engine instruments as the bomber accelerated down the runway. The R-1820 engines produced 1,200 horsepower each at takeoff power, driving the 35,000-pound bomber forward with authority but without the dramatic acceleration of a fighter. The bomber lifted off after a substantial ground roll, climbing away at a rate Lerche characterized as adequate but unimpressive by fighter standards. But this was a bomber, not a fighter. Comparison to German fighter performance was inappropriate. Once airborne and established in level flight, Lerche explored the B-17's handling characteristics systematically. At lower altitudes, the bomber felt exactly as German combat reports had described. It was stable, even ponderous, requiring deliberate control inputs. Turning performance was poor compared to any fighter. Rolls were slow. The aircraft lacked the nimbleness that characterized fighter designs, but these characteristics were not weaknesses for a bomber. The stable, predictable handling simplified formation flying, crucial for bomber operations. The heavy controls reduced susceptibility to turbulence and made the aircraft easier to fly on instruments in bad weather. Lerche climbed steadily to evaluate high-altitude performance. This was where the turbo-superchargers became critical. These devices, driven by exhaust gases, forced additional air into the engine cylinders, maintaining power as atmospheric pressure decreased with altitude. German fighters typically lost significant power above 20,000 feet, as naturally aspirated engines struggled in thin air. The B-17's turbo-supercharged engines maintained full-rated power to much higher altitudes. At 25,000 feet, where a Bf-109 might operate at 70% of sea-level power, the B-17's engines continued producing 1,200 horsepower each. The performance difference at altitude was dramatic. The bomber that had seemed sluggish at lower altitudes became more capable at high altitude. Rate of climb remained adequate. Control response improved somewhat as airspeeds increased in the thinner air. Most significantly, the bomber could sustain operations at altitudes where German fighters had limited combat effectiveness. American strategic bombing doctrine called for operations at 25,000 to 30,000 feet, altitudes where German interception was difficult and flak less accurate. The turbo-superchargers made this doctrine feasible. Lerche conducted controlled tests of the aircraft's single-engine performance, a critical safety characteristic. He reduced power on one engine completely, simulating battle damage or mechanical failure. The B-17 continued flying, maintaining altitude with 3 engines operating. Control loads increased somewhat, as rudder trim was required to compensate for asymmetric thrust, but the aircraft remained manageable. He repeated the test with 2 engines on the same side at reduced power, simulating more severe damage. The bomber could still maintain altitude, though control margins were reduced. This capability impressed Lerche profoundly. German twin-engine bombers could typically survive the loss of one engine with difficulty. Losing 2 engines meant immediate forced landing. The B-17's 4-engine configuration provided genuine redundancy. A bomber could sustain substantial damage, losing 1 or even 2 engines, and continue flying to base or neutral territory. This survivability characteristic explained the combat reports of B-17 seconds returning to English bases with severe battle damage. The aircraft was genuinely difficult to destroy completely. Lerche's post-war account, published in his memoir Luftwaffe Test Pilot, recorded his assessment that the B-17 was completely engineered, meaning every system was carefully designed and integrated. Nothing felt improvised or compromised. The aircraft had been engineered as a complete system, where every element supported the others. The engines provided reliable power. The turbo-superchargers enabled high-altitude operation. The structure absorbed battle damage. The controls remained effective under various loading conditions. The defensive armament protected the bomber. Each system contributed to the overall mission capability. The flight test program continued through February 1943, with multiple sorties documenting various performance parameters. Maximum speed at sea level measured approximately 287 miles per hour. At 25,000 feet, with turbo-superchargers operating efficiently, speed increased to approximately 300 miles per hour. These speeds were unremarkable by fighter standards. A Bf-109G could exceed 400 miles per hour in level flight. But bomber speed was less important than other characteristics. The B-17 was fast enough to make interception by fighters challenging when timing and altitude advantages favored the bombers. Range and endurance impressed the evaluators significantly. With full internal fuel capacity of 1,730 gallons across multiple tanks and auxiliary fuel systems, the B-17 could remain airborne for over 8 hours, covering distances exceeding 2,000 miles in optimal conditions. Combat missions with bomb loads and higher fuel consumption reduced this range substantially, but even combat radius exceeded 600 miles, allowing strikes deep into German-occupied territory from bases in England. By comparison, German bombers had shorter range, limiting their operational flexibility. Rechlin prepared detailed performance charts from Lerche's test flights and the chaseplane observations. These charts plotted speed versus altitude, rate of climb at various weights, fuel consumption at different power settings, and control authority at various configurations. The data filled multiple reports that were distributed through Luftwaffe technical services to operational commands and aircraft manufacturers. The message was consistent. The B-17 was a capable heavy bomber that could operate effectively at high altitude, sustain battle damage, and defend itself with formidable firepower. Rechlin's armament range conducted live-fire tests of the captured B-17's defensive guns in February 1943. Engineers mounted the bomber on a test stand and fired the weapons systematically to document actual performance. An armament officer's diagram overlaid gun arcs on a sphere representing space around the bomber. Bursts were timed with chronograph equipment to measure actual firing rates. Multiple cameras photographed the gun muzzle flashes and tracer patterns to document fields of fire visually. The live fire demonstration validated the theoretical calculations with dramatic clarity. When all 13 guns fired simultaneously, the volume of fire was overwhelming. Tracer patterns created visible streams of projectiles, extending hundreds of meters from the bomber. The combined sound of 13 heavy machine guns firing together was distinctive, a deep hammering roar unlike anything the range personnel had experienced previously. Even more impressive than the raw volume of fire was the systematic coverage provided by the gun positions. The armament engineers constructed a detailed analysis of engagement zones. They divided the space around the bomber into sectors and calculated how many gun positions could engage a target in each sector. Directly astern, at least 4 guns could engage, potentially 6 if the ball turret and dorsal turret operators tracked the target effectively. From the beam, at least 3 guns per side could engage. From below, the ball turret provided complete coverage. From above, the dorsal turret covered most approaches. From ahead, the nose guns provided forward defense, though with lighter firepower than other sectors. The analysis concluded that nowhere in the defensive sphere could a fighter approach without facing multiple defensive weapons. The mathematical probability of taking hits during an attack run was extremely high regardless of approach angle. Even if individual German pilots were skilled enough to avoid being hit during a single attack, the cumulative probability across multiple attacks meant that losses were inevitable. And losses of experienced fighter pilots were irreplaceable, while American bomber production could replace destroyed B-17 seconds within weeks. The defensive system's effectiveness depended on proper crew coordination and training. The armament engineers noted that maximum effectiveness required gunners to track targets accurately, manage ammunition conservation, and avoid conflicts where multiple gunners engaged the same target while other sectors remained uncovered. But combat reports from both German and Allied sources indicated that American bomber crews received extensive training in defensive gunnery. The system worked as designed when crews executed their responsibilities properly. Range notes compiled by Rechlin armorers recorded observations that would influence German tactical development. No survivable stern approach existed for lone fighters at typical engagement distances of 300 to 400 meters. The concentration of defensive fire from tail guns, waist guns, and potentially other positions created a fire corridor that destroyed or severely damaged attacking fighters. Multiple German pilots had reported instances where stern attacks resulted in fighter losses with minimal damage to target bombers. The mathematical realities were unforgiving. A fighter making a stern attack would spend 15 to 20 seconds within defensive gun range, closing from initial firing distance to point-blank range. During this period, the bomber's defensive gunners would fire hundreds of rounds at the fighter. Even if only a small percentage of these rounds hit, the cumulative damage would likely be catastrophic. Fighter aircraft had limited armor protection. Critical systems like cooling systems and fuel tanks were vulnerable. A few hits could disable a fighter even if they did not destroy it outright. The calculations led Rechlin analysts to conclude that emphasis must shift to concentrated squadron attacks and frontal approaches that compressed exposure time. A head-on attack halved the time in the defensive fire zone compared to stern attacks. Though frontal attacks faced their own challenges, including high closure rates and collision risks, they appeared to be the only viable approach that offered acceptable loss rates for German fighter units. This tactical assessment reached operational fighter units through intelligence summaries and technical bulletins distributed by Oberkommando der Luftwaffe. Fighter group commanders received specific guidance on B-17 engagement tactics. The guidance recommended avoiding stern attacks unless overwhelming numerical advantage allowed sacrificing fighters to destroy critical targets. Frontal attacks were recommended despite higher skill requirements. Beam attacks remained viable if executed properly with deflection shooting, but offered only marginal improvements over stern approaches in terms of defensive fire exposure. The tactical revolution that followed emerged primarily from practical combat experience rather than theoretical analysis. Hauptmann Egon Mayer, commanding a Staffel with Jagdgeschwader II Richthofen, operating from bases in Brittany, began experimenting with head-on attacks in March 1943. Mayer was an experienced pilot with multiple victories who understood both the capabilities and limitations of German fighters. He had observed the futility of traditional stern attacks against B-17 formations and recognized that new tactics were essential. Mayer's approach involved careful positioning. His fighters would climb to altitude well ahead of the approaching bomber formation, position themselves at the same altitude or slightly higher, and then turn to attack head-on. The attacking fighters would approach in line abreast formation, not line astern, allowing multiple fighters to engage the formation simultaneously and saturate defensive fire. Each fighter would aim specifically at the cockpit area and nose section, where the aircraft's structural design offered less protection than other areas. The frontal attack technique required precise timing and nerve. Fighters would accelerate in the dive toward the bombers, closing at combined speeds approaching 500 miles per hour. At ranges of 400 to 500 meters, the attacking pilot would open fire, aiming for the cockpit and nose section. The burst would last perhaps 2 seconds. At 200 meters, with collision imminent, the pilot would brake violently, typically diving beneath the bomber formation to avoid collision, and present a more difficult target for defensive gunners during the brake. Major Georg Peter Eder, also serving with JG-2, adopted similar tactics independently. Unit reports from both officers credited successful frontal engagements to reduced exposure to defensive fire. The forward-facing nose guns represented only 2 weapons compared to the 6 or more that could engage from other angles. The brief exposure time, typically 3 seconds total, from opening fire to breaking away, reduced the probability of taking significant defensive fire hits. And aiming at the cockpit area targeted the bomber's most vulnerable point. Penetrating hits on the cockpit could kill or incapacitate the pilots, causing immediate loss of control. Hits on the nose could damage the bombardier and navigator positions and potentially disable critical flight controls. Oberkommando der Luftwaffe circulated tactical notes formalizing Frontalangriff doctrine for B-5, 109G6, and 5 190A series units in spring 1943. The tactical guidance included detailed recommendations on positioning, approach speeds, aiming points, and brake procedures. Emphasis was placed on unit-level coordination where multiple fighters attacked simultaneously rather than sequentially. Sequential attacks allowed bomber defensive gunners to concentrate fire on each attacker individually. Simultaneous attacks from multiple angles forced defensive gunners to divide their attention and fire, reducing the concentration on any single attacker. The new tactics showed improved effectiveness in combat reports from summer 1943. German pilots achieved higher bomber destruction rates per sortie flown, but the tactics came at substantial cost. Frontal attacks were inherently dangerous. Collision risks were significant. Several experienced pilots died in collisions during frontal attacks. Others misjudged the brake timing and took concentrated defensive fire during their attack runs. Pilot casualty rates increased during the implementation period, indicating that while the tactics offered better probability of success than stern attacks, they remained hazardous. The tactical shift also highlighted the weapon limitations of German fighters. The standard armament of 2 7.92 mm machine guns and 1 or 2 20 mm cannons in Bf-109G variants, or 4 20 mm cannons in 20W-190A variants, provided substantial firepower but faced challenges in frontal engagements. The brief firing window in a head-on attack, typically 2 seconds or less, meant that every round had to count. Pilots needed to score concentrated hits on critical areas to achieve bomber destruction. Near misses accomplished nothing. The Luftwaffe began installing heavier armament in fighter variants, specifically to improve effectiveness against heavy bombers. April and May 1943 saw accelerated deployment of the Mk-108 30mm cannon, a powerful weapon that could destroy heavy bombers with relatively few hits. The Mk-108 fired a 330-gram high-explosive shell at relatively low velocity of 540 meters per second. While the low velocity created ballistic challenges requiring careful range estimation and deflection shooting, the destructive effect of hits was enormous. A single hit could sever structural members. 3 to 5 hits could bring down a heavy bomber. Fighter group technical officers worked with armament specialists to install Mk-108 cannons in various configurations. Bf-109 G6 variants received underwing gondola mounts carrying Mk-108 cannons, though these external installations caused drag penalties and reduced maneuverability. Fo-190A6 variants received improved wing installations. The most advanced variants carried multiple Mk-108 cannons, creating devastating firepower packages when hits could be achieved. But the improved firepower came with trade-offs. The additional weight and drag of heavy cannon installations reduced fighter performance, particularly climb rate and turning capability. Ammunition types also evolved to maximize effectiveness. German armorers loaded ammunition belts with specialized projectile types. Menengeschoss rounds, thin-walled high-explosive shells, provided maximum destructive effect against aircraft structures. Armor-piercing incendiary rounds could penetrate armor and ignite fuel tanks. Tracer rounds allowed pilots to observe their fire and adjust aim, though experienced pilots often deleted tracers from their ammunition loads to avoid revealing their position to defensive gunners. Test memoranda from armament facilities noted acceptable cockpit penetration capability at ranges under 300 meters when using Mk-108 cannons. The heavy explosive shells could blast through the B-17's nose section and cockpit area with devastating effect. But accuracy at longer ranges was problematic. The low muzzle velocity of the Mk-108 created pronounced ballistic drop. At 400 meters, the shell would drop several meters below the aim point, requiring significant lead and elevation adjustments that were difficult to judge accurately in dynamic combat. The doctrine that emerged by summer 1943 emphasized short, high-deflection bursts with cannon-armed fighters making frontal attacks. Pilots were trained to close to 300 meters or less before opening fire, accepting the increased collision risk to maximize hit probability. The concentration on short, accurate bursts was essential. Mk-108 ammunition capacity was limited. Bf-109G variants with Mk-108 gondola installations carried only 150 rounds per gun. At a firing rate of 650 rounds per minute, this provided approximately 14 seconds of firing time per gun. A pilot who fired indiscriminately would exhaust ammunition in seconds. Discipline in fire control became as important as marksmanship. Even as German tactics and weapons improved, a more fundamental problem became apparent to Luftwaffe commanders. The B-17's defensive firepower could be countered through clever tactics and heavy weapons. But American industrial capacity could not be countered at all. Intelligence reports documenting American bomber production painted an increasingly bleak picture. Boeing's Seattle plant, Douglas's Long Beach facility, and Vega's Burbank plant were producing B-17 seconds at accelerating rates. Monthly production that had numbered in dozens in 1942 reached over 300 aircraft per month by late 1943. The production statistics were verified through multiple sources. Intelligence agents operating in neutral countries gathered information about factory expansion. Luftwaffe reconnaissance flights photographed American and British airfields, counting aircraft. Serial numbers from captured or shot down bombers allowed analysts to estimate production volumes by tracking number sequences. Prisoner interrogations provided data about new units forming and equipment allocations. Every source confirmed the same conclusion. American bomber production was increasing exponentially, while German fighter production struggled to keep pace with losses. The mathematics were merciless. If Germany shot down 10% of attacking bombers in a given raid, a reasonable success rate given defensive capabilities, those losses would be replaced within days from American production. German fighters lost in combat took weeks or months to replace, as German industry struggled with resource constraints and Allied bombing of aircraft factories. The equation favored attrition warfare for the side with superior industrial capacity. America could afford to trade bombers for fighters. Germany could not afford the reverse. Reichlin's warning that density of bomber formations nullified single-unit success became apparent in combat throughout 1943. American bomber doctrine emphasized formation integrity and mutual defensive support. Bombers flew in combat boxes, three-dimensional formations, where each bomber provided defensive fire to protect neighboring aircraft. A tight combat box might include 18 to 21 bombers in a compact formation, where defensive fields of fire overlapped completely. Any fighter attacking one bomber would face defensive fire from multiple aircraft. German fighter pilots discovered that breaking up these formations required either overwhelming numbers of attackers or accepting prohibitive losses. A single Staffel of 12 fighters could not engage a combat box effectively without suffering heavy casualties. Even a Gruppe of 3 Staffeln, roughly 36 fighters, faced challenges against a properly flown combat box defended by 200 to 300 defensive guns in total. The only effective approach was massed attacks, with every available fighter concentrated against one formation. But this left other bomber formations unmolested. The tactical and strategic problems spiraled throughout summer and fall 1943. American bomber formations grew larger and more sophisticated. Escort fighters began appearing with increasing frequency. The Republic P-47 Thunderbolt, with its heavy firepower and robust construction, could escort bombers to targets well inside Germany. The P-47's arrival changed the tactical equation completely. German fighters that managed to position for bomber attacks now faced interception by escort fighters. Combat losses increased as German fighters fought both bombers and escorts. The Regensburg and Schweinfurt raids in August 1943 illustrated the complexity of the defensive challenge. On August 17, approximately 376 B-17 seconds attacked ball-bearing factories at Schweinfurt and aircraft facilities at Regensburg in deep penetration missions. German fighters engaged the formations throughout their routes, achieving substantial success. Approximately 60 B-17 seconds were lost to fighters and flak, representing roughly 16% of the attacking force. German pilots reported their cannon and rocket attacks destroyed or damaged many bombers. But the raids also demonstrated American determination and capability. Despite heavy losses, the surviving bombers pressed attacks and delivered substantial bomb tonnages on target. Within 2 weeks, replacement bombers arrived in England, bringing American bomber strength back to pre-raid levels. German fighter units that had engaged the raids required weeks to recover from losses. Several experienced pilots had been killed or seriously wounded. Aircraft losses required replacements from production that could not fully compensate. The engagement rates that appeared successful in isolated tactical terms proved unsustainable in strategic context. German depot returns documented the industrial disparity with depressing clarity. American bomber inventories in England that decreased after major raids recovered within weeks through replacement aircraft shipped from the United States. German fighter inventories that decreased after major engagements recovered more slowly despite maximum production efforts. The replacement pipeline was fundamentally asymmetric. American factories produced bombers faster than German fighters could destroy them. German factories produced fighters slower than combat attrition consumed them. The Operational Analysis section of Oberkommando der Luftwaffe prepared statistical summaries in September 1943, comparing American bomber production to German fighter production and combat loss rates. The comparison used documented figures from intelligence reports and operational records. American heavy bomber production in 1943 would reach approximately 9,615 B-17 seconds and 3,629 B-24 Liberators, totaling over 13,000 four-engine heavy bombers. German fighter production in 1943 would reach approximately 10,898 single-engine fighters of all types. The comparison was inherently flawed because it compared dissimilar aircraft types, but the broader implication was clear. America was building heavy bombers at a rate comparable to German single-engine fighter production. The industrial capacity gap was enormous and widening. American bomber production was accelerating faster than German fighter production could match. Even assuming combat conditions remained stable, which they would not, the mathematics favored eventual American air superiority through simple numerical advantage. General Adolf Galland's later memoir captured the strategic assessment emerging in fall 1943. He noted that tactical improvements, heavier weapons, and clever tactics could increase German effectiveness in air combat. But these measures could not change the fundamental equation. The war in the air, like the war on the ground, would be decided in factories. The nation with superior industrial capacity would ultimately prevail through attrition, regardless of tactical brilliance or individual heroism. Germany simply could not produce enough fighters to maintain air superiority against enemies with combined industrial capacity exceeding German capacity by factors of 5 or more. The captured B-17F Wulf Hound continued in German service throughout this strategic evolution. After Lerche's flight testing and Rechlin's technical evaluation concluded in spring 1943, the bomber was transferred to operational units for practical evaluation. The aircraft was repainted in German markings, with Balkenkreuz national insignia replacing American stars. Yellow undersurfaces and tail surfaces were applied according to Luftwaffe practice for captured aircraft to prevent friendly fire incidents from German flak units. The bomber received work number T9+FK in the Zircus Rosarius coding system, the demonstration unit that showcased captured aircraft to frontline fighter units. Documentation indicates the captured B-17 flew additional missions for various evaluation purposes throughout 1943 and into early 1944. Some accounts suggest the aircraft was used for radar testing and electronic warfare trials. The B-17's extensive radio and electronic equipment suite made it valuable for testing German radar detection capabilities and developing countermeasures. Other reports indicate the bomber flew training missions, allowing German fighter pilots to practice attack runs against an actual B-17 target, learning recognition features and practicing aiming points. By late 1943 or early 1944, the captured bomber was transferred to Kampfgeschwader 200, the Luftwaffe's special operations unit that operated, captured, and clandestine aircraft for various covert missions. KG-200's mission portfolio included agent insertion and extraction, clandestine supply flights, electronic intelligence gathering, and deception operations. The unit operated a diverse fleet of captured aircraft, including American, British, and Soviet types, that could fly missions in enemy markings to confuse opposition or access restricted areas. KG-200 flight logs and operational records, fragmented and incomplete as they are in surviving archives, indicate the captured B-17 conducted multiple missions under German control. Some missions involved electronic intelligence gathering flights along Allied air routes, monitoring radio frequencies and radar emissions. Others may have involved deception flights intended to confuse Allied intelligence about German capabilities. The bomber's ability to fly in German markings made it valuable for testing Allied identification procedures and radar responses. The operational use of the captured B-17 highlighted an ironic reality, where Germany exploited one captured bomber intensively for testing, training, and occasional operations over many months. American factories had produced hundreds of new B-17 seconds during the same period. The single captured aircraft was valuable intelligence asset that provided useful data for German tactical development. But American production rendered the intelligence partially moot. Even perfect tactical knowledge could not overcome the numerical advantage American industry provided. The bomber's service with KG-200 ended in April 1944 at Oranienburg Airfield, north of Berlin. Allied air raids targeted the Oranienburg facility, which housed various test and evaluation units, including elements of KG-200. An air raid on April 10, 1944, heavily damaged the airfield and destroyed multiple aircraft. Post-raid damage assessments compiled by surviving ground personnel recorded the loss of several captured aircraft, including the B-17. Whether the bomber was destroyed by direct bomb hits, secondary explosions, or fire is unclear from fragmentary records. The aircraft that had survived combat damage, emergency landing, capture, extensive testing, and operational service was eliminated by the air offensive it could not stop. The fate of Wulf Hound at Oranienburg represented symbolic conclusion to a larger strategic reality. The bomber had revealed American defensive firepower, validated German tactical concerns, and demonstrated industrial capacity through its mere existence. German pilots had learned to respect and fear the B-17's defensive armament. German engineers had documented the aircraft's capabilities with professional thoroughness. German tacticians had developed counter-tactics that improved engagement success rates. But none of this changed the fundamental equation. American bomber production continued at accelerating rates throughout 1944. By year's end, over 8,600 additional B-17 seconds had been built, bringing total production to approximately 12,731 aircraft by war's end in 1945. These bombers, operating from bases in England, Italy, and eventually France, conducted strategic bombing campaign that progressively destroyed German industrial capacity, transportation networks, and oil production. The campaign succeeded not through individual tactical brilliance, but through systematic application of overwhelming material superiority. German fighter defenses, despite tactical improvements and weapons developments, could not prevent American bomber operations. The introduction of long-range fighter escorts, like the P-51 Mustang in early 1944, fundamentally changed the air war's character. American fighters could now escort bombers to any target in Germany, engaging German interceptors throughout the mission. German fighter losses increased catastrophically, as they faced not just bomber defensive fire, but also escorting fighters that held performance advantages at operational altitudes. The statistics from 1944 documented the collapse of German air defense. The Luftwaffe lost approximately 2,800 fighter pilots killed between January and June 1944, an unsustainable attrition rate that destroyed the experienced pilot cadre. Fuel shortages, caused partly by Allied bombing of synthetic oil plants, grounded many German fighters even when aircraft were available. Training of replacement pilots was compressed by fuel constraints, sending inadequately prepared pilots into combat against experienced Allied aviators. The quality gap widened continuously as American pilot training programs maintained high standards while German training deteriorated under resource constraints. The captured B-17's role in this strategic context was ultimately minimal yet symbolically significant. The single bomber provided tactical intelligence that helped German fighter pilots survive encounters with American formations. It validated tactical developments like frontal attacks that improved engagement effectiveness. It demonstrated that the B-17 could be countered through clever tactics and heavy weapons. But it simultaneously revealed the larger truth that German intelligence analysts and commanders had to accept. The B-17 was not merely a weapons platform. It was the visible manifestation of industrial capacity that Germany could never match. May 1945 brought Germany's unconditional surrender and the end of strategic bombing operations over Europe. Post-war interrogations of German pilots and commanders by Allied intelligence services gathered perspectives on the air war. Hans-Werner Lerche, captured by Allied forces, provided detailed testimony about Rechlin's testing programs and captured aircraft evaluations. His assessments of American aircraft were professional and balanced, acknowledging both strengths and weaknesses without propaganda or exaggeration. Lerche's post-war statement about the B-17, recorded in multiple interrogation reports, summarized German perspective on American aviation. He characterized the Flying Fortress as the most completely engineered aircraft Germany encountered during the war. Its strength derived not from any single innovative feature, but from systematic integration of proven technologies into a coherent whole. Every system supported operational requirements: armor-protected crews, self-sealing tanks reduced fire hazards, reliable engines provided power, effective armament defended the bomber, robust structure absorbed damage. The aircraft was designed as a system where every element contributed to mission success. But Lerche emphasized that the B-17's true power was inseparable from the industrial system that produced it. The bomber was formidable because hundreds of identical aircraft flew together in formations that concentrated defensive firepower. The formations were formidable because they could sustain losses and continue operations. Operations could sustain losses because replacement aircraft arrived from production faster than combat destroyed them. Production could replace losses because American industry operated on a scale that Germany never achieved even at maximum mobilization. The final production statistics validated this assessment with mathematical precision. Total B-17 production from 1935 to 1945 reached 12,731 aircraft, built across Boeing's Seattle plant, Douglas's Long Beach and Tulsa facilities, and Vega's Burbank plant. Peak monthly production exceeded 400 aircraft in March 1944. The United States produced more B-17 seconds than Germany produced fighters of all types in some years. When combined with production of other American heavy bombers like the B-24 Liberator, which exceeded 18,000 units, American four-engine bomber production totaled over 30,000 aircraft. Germany produced approximately 119,000 aircraft of all types throughout the entire war, across all manufacturers. The United States produced approximately 324,000 aircraft of all types. The production ratio exceeded 2.5 to 1 in America's favor. These numbers explain the strategic outcome more clearly than any tactical analysis. Industrial capacity determined air superiority. Air superiority determined strategic bombing effectiveness. Strategic bombing destroyed industrial capacity and transportation networks. The collapse of German logistics prevented effective military operations. The cycle reinforced itself as Allied bombing degraded German production while Allied production accelerated. The lesson embedded in the captured B-17 story transcended tactical details about defensive firepower or attack doctrine. The fundamental truth was that modern industrial warfare between peer competitors would be decided by production capacity as much as battlefield performance. The nation that could design adequate equipment and produce it in overwhelming quantities would defeat opponents with superior equipment produced in insufficient quantities. Quality mattered, but quantity ultimately dominated when quality was adequate for mission requirements. The B-17 Flying Fortress was never the best bomber by all measurable standards. Soviet bombers carried heavier bomb loads. British bombers flew faster at some altitudes. German jets flew faster than any propeller-driven aircraft. But the B-17 was good enough for its mission, and America produced enough of them to make individual superiority irrelevant. A force of 12,731 adequate bombers achieved strategic objectives that no smaller force of superior bombers could match. The arithmetic was undeniable. German intelligence officers who examined the captured bomber in December 1942 understood this arithmetic before the war's outcome was certain. They documented the B-17's defensive firepower with professional accuracy. They recognized the tactical challenges posed by 13 heavy machine guns creating interlocking fields of fire. They developed counter-tactics that improved German fighter effectiveness. But they also recognized, though official channels often suppressed this assessment, that tactical brilliance could not overcome industrial disparity on the scale revealed by American bomber production. The decisive discovery at Rechlin was not merely the defensive firepower, though that was significant. The decisive discovery was the industrial system behind the bomber. America could build B-17 seconds faster than Germany could destroy them. American factories produced replacement bombers within weeks. German factories needed months to replace lost fighters. American training programs produced adequate pilots continuously. German training compressed under resource constraints. American logistics sustained operations at any scale. German logistics struggled to supply frontline units adequately. Where Germany exploited one captured bomber intensively over 18 months, extracting maximum intelligence value from every system and component, American plants delivered 10 new bombers before lunch each day at peak production. This was the equation no tactic could solve. Industrial mathematics always prevails in extended conflicts between modern industrial nations. The side with superior production capacity can sustain operations indefinitely while accepting losses that would cripple opponents with lesser capacity. The story of Luftwaffe officers flying the captured B-17 and admitting they had never seen defensive firepower like it reveals this larger truth. The firepower was real and formidable. German pilots paid for that reality with their lives when tactics failed or luck ran against them. But the truly unstoppable force was not the 13 guns. It was the factories that built 12,731 bombers, each carrying 13 guns, each supported by logistics that sustained operations across oceans and continents, each replaced when lost faster than enemies could destroy them. The captured B-17 taught German engineers about American defensive systems, but it also taught German strategic planners about American industrial reality. The lesson came too late to change German strategy. By December 1942, when Wulf Hound landed at Melun, Germany's strategic path was already fixed by earlier decisions. But the bomber provided undeniable evidence of a truth that some German officers had suspected. The enemy they faced possessed not just different equipment, but fundamentally different industrial capacity. This capacity, when applied systematically to military production, created advantages that tactics could not overcome. American engineers designed the B-17 as a combat aircraft that could survive in hostile airspace through armor, defensive firepower, structural robustness, and reliable systems. American industrialists manufactured it on assembly lines that produced one bomber per day at each major plant. American logistics shipped these bombers across oceans to operational bases. American training programs provided crews to fly them. American maintenance supported sustained operations. The entire system functioned as an integrated whole, where each element reinforced the others. Germany could match individual elements. German engineering was often superior in technical sophistication. German manufacturing achieved remarkable output given resource constraints. German logistics adapted creatively to difficult circumstances. German training produced skilled individuals, but Germany could not match the total system operating at American scale. The captured bomber revealed this truth to those willing to see it clearly. The final irony was that the bomber destroyed at Oranienburg in April 1944 had taught its lessons thoroughly, but too late to matter strategically. German fighters had learned to respect B-17 defensive firepower. German tactics had evolved to counter the threat more effectively. German weapons had improved to increase lethality. But German industrial capacity had not increased proportionally. By April 1944, the air war's outcome was determined. Allied air superiority was complete. German fuel shortages grounded many remaining fighters. Strategic bombing was systematically destroying German industrial capacity and transportation networks. The captured B-17 that had revealed so many tactical secrets could not reveal the strategic secret that mattered most. There was no tactical solution to overwhelming industrial disparity, no clever doctrine, no innovative weapon, no skilled pilot cadre could compensate for an enemy that produced 5 times as much equipment across all categories. The mathematics were merciless and final. In modern industrial warfare between peer competitors, factories matter more than fighters. Production lines determine outcomes more than front lines, and arithmetic always wins. If you value fact-based, source-driven military history, consider supporting the channel.